All right, everyone. I want to talk about a few things over the next few films pertaining to a class that is seen elsewhere other than this university called Introduction to College Mathematics. But the mathematics in there is good mathematics in all circumstances, one could say. It's going to be beneficial to us to know not to make errors that we should not be making. There's a lot of good common sense mathematics that probably many people already know, depending upon where they are in their careers in mathematics and what they're studying. But this initially is presented for people in a particular class I'm teaching, and I think it's going to help you very much. For people that are in circumstances where they've seen a lot of this mathematics, some of it's a pretty good reminder to look at some of this stuff. So let's look at some of these films, and let's see what we can say here. Introduction to College Mathematics. I would like to initially talk about, well, just some basic rules that can be really useful to us, you guys. So let's see how we can handle this. So there's a lot of do's and don'ts in mathematics. There's a lot of do's and don'ts in everything. If we're on top of our game, if we know what we're doing and we can do well, there's less chance we can get caught in mistakes that we should not make. That's a big deal for people that are in the medical profession, who are engineers, who are in any profession. We can't make careless mistakes because the results can be devastating. And we all make mistakes. We work to the best of our ability to make as few mistakes as possible. The more we know, the more alert we are, the better chance we have of not making major mistakes. Mistakes do get made sometimes, but we do our best to avoid them. So let's take a look at some rules that'll help us to look at some stuff, some basic mathematics that gets talked about. Oftentimes we're talking about something known as the real number system. And the real number system consists of basically everything on the number line is what it is. And, you know, here's 0, here's 1, here's 2, here's 3, and it goes on to positive infinity. -1, -2, -3, out into negative infinity, and everything in between. The whole number line has no holes in it. Every point on that line corresponds to a number, or we could assign it a number. And with that in mind, every number that is on that line, every point, every amount of the infinite points on that line are called real numbers. The real numbers are very dense. Between any two real numbers is another real number. Well, what are the real numbers composed of? Well, sometimes you got to put the carriage in front of the horse when you talk about this stuff. And we're going to be talking about real numbers quite a bit. Well, real numbers consist of two kinds of numbers. Rational numbers. If you block out the NaL, it's ratio. It's a ratio of two integers. Well, what are integers? We got to talk about that. And there's the irrational, which are not a ratio of two integers. Those two sets of numbers, when put together, comprise the entire real number system. So that's pretty interesting. Integers are a whole piece. Well, we got to sort of put the carriage in front of the horse. Integers are numbers such as -5, -4, -3, -2, -1, 0, 1, 2, 3, ... going on into infinity, and ... going on into negative infinity. They're a whole piece of a number, the integers. Anytime you can write a number as a ratio of two integers, it's called a rational number. When you cannot, it's called an irrational number. Underneath the rational numbers, there are, well, we just saw what I just said here. They're the integers. They are a subgroup, a subset of the rational numbers. Underneath those is the whole numbers. Now the whole numbers are just the right-hand side of the integers with 0 in them. So whole numbers are 0, 1, 2, 3, ... going on forever. And the natural numbers, oftentimes known as the counting numbers, the natural numbers and they're 1, 2, 3, ... And that's all under the category of rational numbers, you guys. So let's make sure we, that's not, the irrational is kind of, well, whatever the rational numbers are not, those are the irrational numbers. So this is all under the category of rational numbers. So let's write this. So, and like I said, those who have had me at various places, various schools, and have seen me teach, I oftentimes go into discussing this sort of situation. So all of these, like I said, all of these are rational numbers. Integers are rational numbers, whole numbers are rational numbers, natural numbers are rational numbers. These are smaller subgroups of the big subgroup, rational numbers. This right here, yeah, there's different categories of this as well. Let's not go there. The big thing is, both of these comprise the entire number line of numbers, the real numbers. It'd be kind of neat to talk about some things, some basic operations we can talk about regarding this. Well, frequently, I guess it's hard to know what's the best way to do some of this. I guess you could say, let's start here. Let's talk about multiplication of real numbers. Let's talk about division of real numbers. Let's talk about addition of real numbers. And let's talk about subtraction of real numbers. And that's usually that's a lot of what we use in some of the basic mathematics that goes on. So, of interest. Well, definitely of interest, and definitely a lot can be said. As we say here, guys, there's sometimes short answers to much of what we're doing. We know that if you multiply any two real numbers, and one of those real numbers is 0, the answer is 0. If you divide any two real numbers, and one of them is 0, and the number being divided is 0, and the number doing the dividing is a non-zero number, the answer is 0. 0 divided by any real number other than 0 is 0. And the other way, any real number divided by 0 for our purposes is undefined. Okay? So 0's got some interesting qualities. When you multiply any numbers and there's a 0 in the multiplicative array, the answer is 0. And when you divide 0 by any number other than 0, the answer is 0. And if you divide 0 into something, for our purposes, it's undefined. So well, that's good enough for me for right now. Otherwise, for any of these real numbers that we're talking about, if you multiply two positive real numbers, you get another positive real number. If you multiply two negative real numbers, you also get a positive real number. If you multiply two real numbers that are opposite in sign, regardless of the order in which you multiply them, you get a negative answer. That's pretty interesting. Division, it's completely analogous to that. With multiplication, when you multiply or divide, with multiplication, if you multiply two numbers with the same sign, both positive, both negative, you get a positive answer. You multiply two real numbers with opposite signs, you get a negative answer. Division's kind of the exact same argument. You divide two positive numbers, get a positive answer. Divide two negative numbers, you also get a positive answer. Divide a positive by a negative, or a negative by a positive, negative answer. Well, there's something interesting here. Regardless of what you do, regarding how the game is played, regarding signs, regarding after an operation is performed, if you multiply or divide two numbers with opposite signs, you get a negative answer. If you multiply or divide two numbers with the same sign, you get a positive answer. Well, let me say that maybe a little more smoothly. If you ever multiply or divide two numbers with the same sign, you get a positive answer. If you ever multiply or divide two numbers with opposite signs, you get a negative answer. So positive answer is attained when the signs are the same in the multiplication or division, and negative answer is attained whenever there are opposite signs in the multiplication or division. So you saw that right here. If you add two positive numbers, you tend to get a more positive answer. You will get a more positive answer. If you add two negative numbers, you'll get a more negative answer. I went to Las Vegas. I lost $500 the first game. I lost $1,000 the second game. If you add two negative numbers, it results even more negative. A loss of 500 and a loss of 1,000 is a loss of 1,500, like that. When the signs are opposites, doesn't matter which one you're adding first, you could get 0, negative, or positive. The number with the bigger absolute value, its sign dominates the answer. You just make them both positive in your mind, do a simple subtraction to get a positive answer, and then just say, okay, is that negative or positive? You take two numbers, if they're of opposite sign, just pretend they're both positive, do a subtraction, whatever's most convenient, to give you a positive answer. And say, okay, now that answer is either going to be, or you get 0. That answer is going to be 0, positive, or negative. I just got to look what number had the bigger absolute value. Negative 1,000 and positive 500 add up to, well, negative, let's put it another way. Negative 1,000 plus positive 300 is negative 700. The negative 700 has the negative 1,000 has a bigger magnitude, a bigger absolute value, so it dominates the answer when we do something like this. And it's just the same logic all the way throughout. Whatever one's got the bigger absolute value will dominate the answer. If they both got the same absolute value, negative 1,000 plus positive 1,000, same absolute value, they cancel completely and it's 0. Subtraction's pretty easy to do. Convert it to addition and just do everything that I did right here. Do everything that I did right here for subtraction once you convert it to addition. Any two real numbers, A and B, doesn't matter what their sign is. One could be positive, one could be negative, one could be 0, anything. Any two real numbers, when you subtract them, it is the same as adding the opposite of the number that was being subtracted. A minus B is A plus the opposite of B. Every subtraction could be turned into an addition problem. It's kind of interesting. Every subtraction could be turned into an addition problem. The addition problem could be turned into a subtraction problem. It may not be convenient, but addition and subtraction, one could describe the other. Every subtraction problem can be made into an addition problem. We saw that right here. And every addition problem can be made into a subtraction problem. Every multiplication problem, you could make it into a division problem. And every division problem you can make into a multiplication problem. It's done quite a bit. Perhaps this is a good time to go to that segue regarding something like that. So let me see here, guys. Let me move this. So, there's a lot to say. Basically, if I had, well, there's a lot you could say. I guess you could say here. If I said to you I was taking the number A and dividing it by the number B, that's the same as A divided by 1 times 1 over B. When you multiply two fractions, you multiply the numerator and you multiply the denominators across and you get that. Well, here you go. I just took a division problem and I made it into a multiplication problem. Fascinating how that can work out. If you look at, if you were to take A over B, two real numbers, any real number, depending upon, regardless of sign, Typically, we don't put 0 in the denominator to try to handle these matters. Well, I already told you how the number 0 behaves in multiplication and division. So everything else, other than those circumstances I described, are fair game. If you got A over B and you're dividing it by D over C, two fractions like this, regardless of signs or anything, a fraction divided by another fraction is the first fraction multiplied by the reciprocal of the second fraction doing the dividing. And you could say, okay, A times C is AC, B times D is BD. You could write it like this. And this is the problem. You know, you multiply the top number is called the numerator, the bottom number is called the denominator. You multiply the numerators across, get a new numerator. You multiply the denominators across, get a new denominator. So numerators multiplied across, new numerator, denominators multiplied across, new denominator. So this has some very fascinating, very interesting applications when we want to do all this stuff. Whether we're talking about fractions, mixed numbers, decimals, you name it. You make up any look of a number that you want, we're talking about real numbers. For our purposes, dealing with these real, if you got real numbers and they're in some kind of decimal format, they're positive, they're negative, they're 0, they're small decimals, big decimal type answers, mixed numbers, fractions, they're all in the category of real numbers. And all these rules apply when you're playing that. Okay? So, with that having been said, let's take a look. Let's take a look at some more stuff, how you'd want to look at some of this stuff. There are a lot of things you can say, a lot of rules, as we said. Let's talk about rules. Okay. So what is there to say? What can we say? Well, there's a lot of rules, guys, and there's times you can do things and then not do things. Try to keep it relatively brief and get into some other, those who know me and have dealt with me, you've seen me handle this in maybe different circumstances. But let's talk about a few things that could be, that should be, I hope, of interest and really something that's top of mind for us, that we're always thinking about. There is the idea that it doesn't matter, if I were adding real numbers, you guys, let's say 3 real numbers, it doesn't matter how I associate the addition. I haven't changed the order in which they're written down, but I could say A plus whatever this quantity is the same as this particular different quantity attained by adding here plus C. This is called the associative property. For multiplication, it'd be something like this. I could do this first, or I could do this. But it doesn't matter which one I do. Whatever this answer is times C is the same as this by itself times BC. That's known as the associative property. Okay? That's the associative property of addition and multiplication. As we said, all subtraction can be made into addition. All multiplication can be made into division. So basically, they only have to talk about addition and subtraction. Forgive me, they only have to talk about multiplication and addition, and we can get to a discussion about division and subtraction, because I can get to all division through multiplication, and I can get to all multiplication through division, actually. I can convert multiplication to division. I can also, in an awkward way, convert division into multiplication. Multiplication to division, division into multiplication, same thing here. I can make any sort of addition into a subtraction problem. I can make any subtraction problem into an addition problem. So this is basically the associative property. Now, they got this other thing, and that's this. And we've got this other thing. If you got A times B, it's the same as B times A. And like I said, let me kind of do the order here. I was doing the addition first. Doesn't matter the order that I add two things. You can pay me my money with $30 first and then the other $70 that you owe me to give me $100, or you can give me the $70 first and then the $30. Doesn't matter the order in which you pay me, the money's going to be the same. So that's the commutative property, and then for multiplication, doesn't matter the order that you multiply two things. Pretty fascinating stuff. A little more, it's a little deeper than one might think it is when you look at it. And those of you that have been in classes that I've taught, you see sometimes I try to look into how that plays out. So that's associated with commutative. The distributive property is basically if you got A times some quantity, B plus C, let's say, you can basically take that A, these are real numbers now, any real numbers, and you can get AB plus AC. It's known as the distributive property. It's pretty interesting stuff. This works for multiplication and division. If you got B plus C, the whole quantity, and you got it divided by A, the A will go into each of these separately, fully, and then you can add those two divisions that have taken place. Also associated with the distributive property. Also associated with the distributive property. This is very important. There's so many do's and don'ts. Yeah, great, this works. This is true. The distributive property only works for multiplication and or division going on across a sum or subtraction. Basically, if there's addition or subtraction going on and you want to distribute something across the addition or subtraction, the addition stays and this A right here hits each item, and the addition stays. Here there's an addition going on. You're dividing A. It hits each item, and there's an addition going on at the end of that. That's true. This, however, is not true. You cannot go, okay, well, I know what he said. It's A times the quantity BC. Let me take this and let me distribute it. No, don't ever do that. That is absolutely not true. It's not going to be AB. AC. Not going to happen. Can't happen. There has to be addition and or subtraction going on for there to be a distribution associate. If there has to be addition or subtraction going on for you to be able to distribute when there's going to be multiplication or division. I can distribute because there's addition or subtraction going on, either for the multiplication or for the division. For division, I can do a distribution, get this. For multiplication, I can do a distribution, get that. There's straight out multiplication, you can't do that. What you can do is, it only hits one place. It hits the B. That's it, you're done. Or it hits the C. So here's, let me see here. So this is, this is not true. This is not true, you can't do it. But what you can do is this. You can have the A hit the B and that's it. Or you can have the A hit the C. But it only hits once. And that's very important. That's very important, especially when there's symbols around. You've got to watch out for what's going on. There's like a great problem I talk about, and I have it in various places. in learning management systems at different schools where I've taught and teach. I have it in different places where I talk about the do's and don'ts. There's a do's and, that's the do's and don'ts thing that we talked about some time ago. The do's and don'ts pages that I talked about talk about, you just can't do certain things. You're not ever going to distribute when there's straight out multiplication or straight out division going on and no addition or subtraction present. When there's no addition or subtraction present, as there's not right here, when there's no addition or subtraction present, you're not going to distribute. Same thing here. When you got the BC here, let's say instead of B plus C, it's just BC. Say, oh, gee, I know what he said. He said this. I said this if there's an addition going on. You cannot do this. Absolutely cannot do this. What you can do is the A can go into the B, or the A can go into the C, and they're equal. But it only goes to one place. It only hits once when there's multiplication and or division going on only. It's a very important thing to know in algebra, especially when there's a lot of symbolic material going on, a lot of symbolic discussion going on. So that's a lot of what's happening that way. And there's other rules, and let's talk about some more rules and see what we can say here, at least for the beginning of this, to give ourselves a look here. To what degree I want to take this, we'll see. I mean, like I said, anybody has questions, can always try to see me. You can always see me in person. So on this, and of course more complicated material when we're doing this. So what we have here, let's see what we can do. Kind of hand in hand a little bit with some of the stuff that we talked about, what you can do with. Let's say there was like some sort of polynomial expression going on here, guys. And, let's say I had, kind of putting the carriage in front of the horse on this one. Let's talk a little bit do's and don'ts with exponents, I guess you could say at this point. Generally, if you've got the same base, the same letter on the bottom, and you take it to the 0 power, and there's exceptions to every rule here, guys. We'd have to look at it. But for our purposes, if you take a real number to the 0 power, a real number exponentiated to the 0 power, for us it's 1. X to the 1 is just x. If you take x to the m, any real number actually, this is true for any real number, and you take x to the n and you multiply these two, you're adding the exponents. People say, wow, it seems like you got to go m times n. Well, not really. Because if I had, for example, if I had x to the third times x to the second, I'm not going to go 3 times 2. This is exponentiation. There's a big difference here, guys. There's a lot going on here. If I were to multiply x by n, I'm going to write down x, and I don't want to get into all the what if scenarios here, guys. But if I were to take this is n terms added together. Multiplication is repeated addition. Exponentiation, x to the n, there's still going to be n terms here. There's still going to be n terms here. Or n items, n factors. N factors. But it's multiplication. It's a big difference. Exponentiation, taking something to a power, exponentiation is repeated multiplication. Multiplication is repeated addition. Let's say it again. Multiplication is repeated addition. Exponentiation is repeated multiplication. The difference is night and day. So if you were doing 3x times 2x, well, remember what I said, you can't do any distribution here. You can only hit things once. Well, let's hit each one of these guys. Let's hit it once. 3 times 2 is 6, and then there's x times x. Well, x times x is x squared. That's it. It's the end of the story. This is a little different dynamic. This is x times x. How many x's are here? X times x times x times x. There's 5 of them. There's not 6, there's 5. So we got to watch out. We have to be on our game. That's why that's true. If you got x to the m over x to the n, m and n can be any real numbers. There's a lot of application and subtlety to that as well. Let's talk. If I had x to the 6th divided by x to the 2nd, there's 6 of these x's in a multiplicative array, and there's a lot, 1, 2, 3, 4, 5, 6, and there's 2 of these x's here. Well, this is true. There's a lot of mathematical subtlety as to why that's true. Yeah, I mean, a lot of people can tell you, oh yeah, sure, well, whatever. Well, there's more to it. This is x to the 4th. Notice, what is 6 minus 2? It's 4. And that's what I'm saying way over there to your far left. It's a different dynamic if you've got this. 6 apples divided by 2 apples. Well, how many groups of 2 apples are there in a bunch of 6 apples? I got 3 groups of 2 inside of here. The answer is going to be 3. Tell you what, let me just cancel just to be safe. 2 goes into 6 3 times. 3 times 1 is indeed 3. Yeah, absolutely. 6 apples, how many times does 2 apples? Apples. Yeah, it's a different dynamic. So don't sit there and don't be dividing the m and the n. Do subtraction. When there's, it's got to be the same letter on the bottom, or the same letters. It's got to be absolutely identical. Don't be multiplying here, be adding. Well, when would you multiply? If you were exponentiating an exponentiated quantity, then you multiply exponents. And there's other things that go on. There's some, I don't know. Some of this stuff you're not really going to need really up front, but I may just touch upon it really quickly just to kind of make some interesting points, I hope. If I were to say to you, now why is that a multiplication? Well, if I had x to the 2nd taken to the 3rd power, 2 times 3 period. Is that true? Well, let me see. X to the 2nd taken to the 3rd power is x to the 2nd times x to the 2nd times x to the 2nd. Then we say we add. 2 and 2 is 4. X to the 4 times x to the 2nd. X to the 4 times x to the 2nd. 4 and 2. So 2 times 2, x to the 2, x to the 2, add those, x to the 4. X to the 4 times x to the 2. 4 and 2 is 6. Tell you what, if you don't really believe it, there's 2 x's there. There's 2 x's there, and there's 2 x's there. There's a total of 6 x's. That's x to the 6th. And that's what happened up there. That's what happened up there. A lot going on here. Like I said, some of this stuff I'm going to go a little bit faster than in others because it may not be something you're immediately going to be seeing or worried about, but at least I want to at least give you some background on it so you're kind of aware of some of the subtleties that are going on here when we're doing this stuff, you guys. So let me see what else we can say about this. How this plays out, there's, like I said, to really do justice to this, to a lot of the topics that I'd like to discuss, it would take a lot more time than we actually have. So I'm at least going to try to touch on some stuff and make it make a little bit of sense, I hope. There's a lot to be said. There's always the idea, you guys, there's always the idea of the do's and don'ts. What you're going to do, what you're not going to do regarding some of this stuff. So let's see what we have. And again, it's in that handout that I gave to a lot of people in different places, different courses and stuff. And you have it as well. I mean, if you want to look at it, you should have it. I mean, if you've had me as a teacher in a number of places and circumstances, it's something I frequently show, some of the do's and don'ts. If somebody were to say to you, again, like let's say negative 3x squared y to the 9th z to the 4th times whatever, you know, you can kind of make it up as you go along here, I guess. 9x y z to the 10th minus 20 x to the 5th y to the 9th z times a plus 40 a x z to the 4th, something like that. Say, wow, I'd like to kind of simplify something like this, polynomial expression or something. Well, again, all the rules that we've made or that we've discovered or that we're told are true and that we know are true, we have to be able to apply them. So if you're looking at this minus 20 x to the 5th y to the 9th z a, minus 20 is plus a negative 20. We know that from the past. Well, this is, you know, way out there. Let me make everything into addition and let me see where this thing goes. So let's see what I can say here, guys. So when you do this, I'm going to put basically, let's not get too fancy. Let's just put everything next to each other. And we got, again, we just have to be on our game here, guys, when we're doing this stuff. Okay, I made this a little, you know, rather, hopefully somewhat interesting. I converted everything into addition. Converting everything to addition is not a bad way to do stuff. It's a good way to do your bookkeeping. Subtraction can be a little bit potentially confusing. You might kind of lose track of stuff. If you just right off the bat took the negative right here, rather the minus 20 x to the 5th y to the 9th za, the minus 20 x to the 5th y to the 9th za, and made it plus a negative 20 x to the 5th y to the 9th za, and then just do the distribution. You saw me do the distributive principle. How am I justified doing the distributive principle? I'm allowed to do it because I am distributing across all the addition or subtraction. I'm allowed to do that. Yes, absolutely true. Once you've come to here, however, it's sort of the end of the line. I know I get it. There's an addition right here. There's an addition right here, and I did all the distribution I was supposed to do. This guy went all the way across, there he is, and went to here, went to there. I get it. True. Now, take care of that. Take care of that. And take care of that. Yeah, I'll take care of it all right, but there's one thing here. I'm not going to do any more distribution in any one of these three packets. This packet, that packet, and that packet. In this multiplicative array, and that multiplicative array, and that multiplicative array, I'm not doing any more distribution. Why is that? Because there's no addition or subtraction present. You're only hitting everything once. Another thing you got to look at. If this was x to the 0, it would be 1. Didn't we say x to the 0 is 1? Not x. X to the 1 is x. So if there's a letter by itself, there's a 1. on top of the exponentiation. It is as simple as that. All right? We are not distributing. We are multiplying anywhere we want to multiply, but once we do multiply, we're done. Once you multiply, you hit it once and you're done. Go like with like, and it should be pretty easy. What is a negative 3 times a positive 9? It's a negative 27. What is x squared times x to the 1? Well, this is one of the x's, this is two of the x's, there are three x's there. What's 1 plus 2? It's 3. Don't go 1 times 2. 1 times 2, yeah, 1 times x to the 2 is x to the 2. That's not a 1, it's x to the 1. It's 1x, and there's 2 x's here in a multiplicative array, and there's 1 x here. There's 3 x's in a multiplicative array. Y to the 9th, y to the 1, 1 and 9 is 10. Z to the 4th, z to the 10th, z to the 14. Negative 3 times negative 20 is positive 60. X squared times x to the 5th, 2 and 5, when you do the multiplication, based on the rules I just showed you, y to the 9th, y to the 9th, 9 and 9 is 18. Z to the 4th times z to the 1, 4 and 1 is 5. And the a to the 1 is just a to the 1, or you can just call it a. That's not a big deal. Let's go over here. Negative 3 times 40 is negative 120. X squared times x to the 1, 1 and 2 is 3. A to the 1 is just a. It doesn't matter where I put it. Let's just put it somewhere, though. Y to the 9 is by itself. I got to leave that. Z to the 4, z to the 4. 4 and 4 is 8. You know what? I'm done. And I can't really simplify this any further, you guys. This is the final answer on this whole thing. Why can't I go any further? You can only add the same kind of fruit to simplify. Don't get me wrong. Don't let anybody tell you that you cannot add these 3 items. Yes, you can, and you just did, and that's the answer. You just can't simplify any further. It's like me saying to you, I have 10 bananas and 3 oranges and 5 apples. 10 bananas, 3 oranges, and 5 apples. That's 18 pieces of fruit, but they're not 18 banana oranges apples. They're not banana orange apples. They're not 18 banana orange apples. They are. Now I forgot which one was which. Right? We said we had 10 bananas, 5 oranges, and 3 apples. Okay, that's whatever. That's not a really big deal. The big thing is I can't take that any further. If I got 10 bananas and let's say 5 apples, I know I'm changing this every time, guys, just bear with me. 5 apples and 3 oranges. I don't want to put an O here. It looks a little odd. Let's put R for orange, okay? Yeah, this is true. I added them. I do have 18 pieces of fruit. I just don't have 18 of a special kind of fruit called a banana, apple, orange. No, it's just 10 bananas, 5 apples, 3 oranges. The only way I can add them together is if I got 10 bananas in a basket, and then I got 5 bananas added onto it, then 6 oranges added on to 3 oranges. That's a different dynamic. 10 bananas and 5 bananas is 15 bananas. 6 oranges and 3 oranges is 9 oranges. End of the story. They're not oranges squared. Notice when you multiply or divide exponents, look at here. We were doing multiplication here, and the exponents, y to the 9th, y to the 1, exponents got bigger when we were multiplying. They tended to get bigger when we were multiplying. And when you divide, exponents tend to get smaller. But when you add, exponents never change. exponents never change once you get down to adding items together. This was a banana, this is a banana. You don't get a new kind of banana called a square banana when you add these two. You do get a square banana if you multiply like this. 10 times 5 is 50. Banana times banana, okay. Well, that's 50 bananas squared. Okay, you do get a square banana. You get a differentiated quantity different from what you had before. That tends to be the case when you multiply or divide. But when you add or subtract, the exponents associated with the variables don't change. Very important. And you saw what we did here. You could have, I mean, and that's, there's a lot here, guys. There's a lot more than, just a lot to say. I mean, there's just a lot to say. I'll try to at least give you some of the basis on this. I've already, those of you who have seen me in person, we've talked about this stuff, you've already seen me go into this early on in classes to some level, depending upon the class. If it's a more basic class, yeah, I've done so. Other times I've said, okay, take a look at some of the films that are out there, or maybe we can talk about it if there's still an issue. But if there was 10 apple cubed banana to the 5th, times C, cupcake, and there's another one, 15, it's called cupcake squared, cupcake squared. Well, wait a minute, if these are identical, same letters, same exponents, you add or subtract the fronts. These are called the coefficients. You add or subtract these. 10 and 15 is 25, and the boxes don't change. There was 10 boxes of this type, 15 boxes of the same type. So 10 boxes of this type, 15 boxes of the same type. When you add them together, it's going to be 10 and 15. It's going to be 25 boxes of the original same type. It's as simple as that. It works that way, you guys. It's got to be exact, though. Exact letters, exact same corresponding exponents. If you ended up putting, instead of a 5 here, a 2 here, and here you ended up putting the 5 right here, no dice. You can't do it. Well, I mean, you can. You add it. You can certainly add them, but it's just 10 boxes of one type, 15 boxes of the other type, a total of 25 boxes, but I'm not making them 25 boxes of this or that. It's just 10 boxes of that, 15 boxes of this. You can't go any further. You have to have the exact same trailing portion for this stuff to work. It's pretty important stuff when you do this for for different people looking at different things. If you're looking, anytime you're looking to build into more higher mathematics, you've got to have these basics under control. There's a lot to be said. I mean, I'll say a couple more things and we'll take it from there. Let me just check really quickly where we are. I want to kind of have a certain time frame in mind when I'm doing this. So far, not bad. So, let's see what we can say here. We'll see at what level we're doing some of these problems, you guys, how many we're going to do when we get into some of the practice exams that are there. Not necessarily having to do all of it, just maybe some of the harder problems that are there. And I think if we can do the harder problems, sometimes we can also do the easier problems. So we'll see what we can do easily. There's a lot that gets said, and I don't know how far I want to go, guys. I can just say, if n is a positive real number, x to the negative n is 1 over x to the positive n. That's interesting. And that's not to be confused with something else. That's not to be confused with this. X to the 1 over n. That comes from the nth root. That comes from, so let me just be careful here, guys. That comes from the nth root of this. Pretty interesting stuff. I'm not gonna beat these are two different things. This is x. This thing. this is x to the 1 over n, and that's the nth root of x. This is 1 over x to the n. There's two different things. Okay. So, like as I said, there's a lot gets said, guys. I'm not going to maybe emphasize everything too greatly when we do some of this stuff. Let me see what I can say here. If you were to take the quantity a times b and take it to the nth power, any real number, it could even be a negative number, it's the same as the n coming inside as an exponent and being on top of every factor as an exponent. So when there's multiplication going on, if you take a quantity that is a product, this product right here, and you exponentiate it, it's the same as the product of the individual factors, exponentiated. So the exponentiation of the product is the product of the exponentiations. The exponentiation of a quotient is the quotient of the exponentiations. Power is probably a better way. The power of a product, a product taken to a power is the product of the powers. A quotient taken to a power is the quotient of the powers. Looks like this. For this right here, it's a little more complicated. We're not going to, like I said, I'm not going to beat it up too badly. But if you had x to, let's say, the m power, and then you took that x to the m and then got the nth root, they write it like this. And actually, that right there is the same as, you can take the m and put it on the outside and have this guy go on the root on the inside. In other words, you could say the root of something exponentiated is the same as the exponentiation of the root, and it's still this. In all circumstances, it becomes something like this, that's x to the m, the whole thing to the 1 over n. X to the m, the whole thing to the 1 over n is the nth root of x to the m. And that's the same as x to the 1 over n taken to the m, and that's the same as this. Something to know, something to look at. It works. It's a brilliant notation. It's some brilliant logic that they use, and it's very consistent. It works. Okay? For our purposes, we know it. At least we're going to say we know it, and we have it here. At least you can get a look at what's happening here, you guys, when we're looking at this stuff. Okay? These two are identical. This one is the same as this one here. Far edge is the same as this lower one, and that's equal to that. And this one is the same as this one. And again, they're the same. All of this is the same, you guys, when we do this. And they're all kind of born from this, I guess you could say, when you want to look at it. Okay? So, very, very, very fascinating stuff. There's some don'ts. Yeah, what I said here is true. What I said here is absolutely true. Everything we said here is true, guys. It works mathematically. It's some strong mathematics. It gets us to where we got to go. Okay, fine. Does that mean I can do this? If I take a sum or a difference and exponentiate it, is that the same as a to the n plus b to the n? No. Same thing here. It's not the same. Forgive me, I might be blocking here. Not the same as those two. You can't do this when there's addition or subtraction present. You can do it when there's multiplication and or division present only. When there's multiplication and or division present only, you can do this. When there's addition and or subtraction present, you can't do that. And it's very similar with roots too. I mean, you say, I already hit this idea of looking at roots and stuff and how this plays out right here. But let me kind of see here. So this is kind of the granddaddy of the whole thing right here. You got these two and how they equal that and everything else we want to play here. So if you have any root, the square root, third root, you name it. If you take the nth root of a product, the nth root of a product is the product. Pick it up. The nth root of a quotient is the quotient of the nth roots. The nth root of a quotient is the quotient of the nth roots. The nth root of a product is the product of the nth root. Looks kind of sort of similar to what's going on here. Yeah, very similar. Here's straight out exponents looked at in such a manner that, okay, you feel pretty good about it. And okay, so here's with exponentiation, some of the games we can play. You're basically playing the exact same kind of when you're talking about roots. And the nth root could be the square root or any kind of root for that matter. The root of the product is the product of roots. The root of a quotient is the quotient of roots, but you can't do that if there's addition or subtraction going on, just like you couldn't do it over here when it was happening. Okay? So, some stuff to look at regarding that. What else did I want to say here, guys? Looking at this, let's look at some, we talked about some of the rules of adding and subtracting and things of that nature. Let's take a look at multiplication of fractions, division of fractions, addition of fractions, addition of real numbers, subtraction of real numbers, things of that nature. Well, let's say they're mixed numbers. Mixed numbers are fractions. How do you add them? How do you subtract them? How do you divide them? How do you multiply them? So just watch what's going on, what you're allowed to do and what you're not allowed to do. So let me just say this to kind of give us a little bit of a feeling for what's happening here. Obviously, guys, any introduction to any mathematics is never really fully complete, given the richness of the mathematics that's all out there. But we have to have certain things under our belt, feel pretty good about it, if we're going to be doing some basic mathematics that's going to be happening. So let's see what we can say, and let's see how it plays out. All right, guys, so there's a lot to be said. I mean, when someone says to you, let's kind of go to the hardest part first, like it makes it a little easier. If I were to say to you 5 2/3, I've got 5 cakes and another 2/3 of a cake. Well, I got more than 5 cakes, but less than 6 cakes. 5 2/3 cakes is between 5 and 6 cakes. If I were to add the opposite of 5 2/3 on each side, that's going to come out to 0. Yeah, okay, we know that. Yeah, maybe there's a lesson to be learned here of what you can do and cannot do. First of all, whenever you add or subtract mixed numbers or fractions, the easiest, perhaps not the easiest, but maybe the safest way to do such operations is to say, you know what, let me make everything into fractions. Whenever you're adding or subtracting fractions, you always have a common denominator. Whenever you multiply or divide fractions, you don't need a common denominator. So if I'm going to add or subtract fractions, I need a common denominator. Well, I want to see these cancel out. They take the big number, 5, multiply it by 3. 5 times 3 is 15, plus 2, 17 over 3. This better be negative 17 over 3, because when I add them, you always keep the denominator untouched, and you add the tops. 17 and negative 17 is 0. And we said it was going to be 0. Be careful. How could we make a big mistake here? Let's purposely make a mistake, but not make this mistake. Somebody might say, hey, negative 5 times 3 is negative 15. Negative 15 plus a positive 2 is negative 13. There's no way negative 13 is going to cancel with 17. Well, how do you do it? To be careful, you always block it off in your mind or with your hand. You block off the negative, and you go 5 times 3 is 15, plus 2 is 17. That's 17 over 3. Oh, it's a negative? That's a negative. That'll work. It's the safest way to do this stuff, guys. Whenever they give you negative 5 and 3/13, what they mean is it's negative of the quantity 5 and, forgive me how I said, I think I said something wrong here. Negative 5 and 2/3. That negative 5 and 2/3 means negative 5 and 2/3. It means negative 5 plus 2/3. It means negative 5 plus negative 2/3. It's a lot of stuff. It means 5 and 2/3. Let's go back to 5 and 2/3, I guess. It means 5 and 2/3, the whole quantity, but the entire quantity has a negative in front of it. 1, 2, 3, 4, 5. Yeah, about 5 different ways you can look at it. No, you're dealing with the whole piece of what's going on there when you want to deal with this stuff, okay? So just be careful, get an idea, get a gut feeling for what's going on. There's less chance you're going to get fooled. You're going to make mistakes sometimes. Every human being makes mistakes sometimes. Oftentimes we get lucky, so we can get away with the mistakes sometimes. Sometimes we don't. So we got to be careful. Try to minimize the mistakes as much as possible, and that's it. Just really pay close attention in everything that you do. Very important. Well, I said a lot here regarding that, so let's see how some of this would play out. I guess you could say we could kind of make up So, see what I can do here, guys. I got what I got. Let's say, there's a lot you can make up, I guess you could say. Let's say I made up, well, let's take our friend, the negative 5 and 2/3, I guess, and let's add him with positive 7 and 1/8. And then I might want, after that, I might want to say, there's a whole lot I could say with that. I could do that. I could also say negative 5 and 2/3 minus 7 and 1/8. I might want to do that problem. I might want to take negative 5 and 2/3 and multiply it with positive 7 and 1/8. And I might want to take a lot of things I could do here. I might want to take 7 and 1/8 and divide it by negative 5 and 2/3. Let's see how that all plays out. Okay, so number of items here, number of things we can do. Well, I tell you what, guys, the big thing is I'm just trying to give you a gut feeling for what's going on with a lot of what is going on here. Let's look at this. Let's try to get a feeling for where this stuff should go, so then when we do this, if we do make a mistake, we can catch ourselves, So let me think here, guys. So I'm going to have to get a little more chalk, I think. Okay, so, my gut feeling, well, this is a negative number. It's more negative than just 5. It's more negative than negative 5, but not as negative as negative 6. It's a negative number between negative 5 and negative 6. This is a positive number a little bit bigger than 7. If I add something bigger than 7 with something that has a magnitude less than what this magnitude is, it's going to be some kind of a positive number when they do the tug of war. If I got 7 1/8 cakes and you want me to give you 5 2/3 cakes, well, yeah, I'll still have some cake left over. I might have one left over or something like that. Here's a different argument. I own a business. I owe this particular company, because I didn't deliver the last time I was working with them, I owe them 5 2/3 cakes, and then they're also going to take 7 1/8 cakes from me as a penalty if I want to stay in business with them. So if I lost 5 something and I lose another 7, a loss of 5 and a loss of 7 is a loss of 12. So maybe a loss of 12, loss of 13. So this is like negative 13 or so. This is like positive 1 or so. What's a negative times a positive? We already talked about this. A negative times a positive. See, nothing's really going to, these signs don't mean a whole lot. If that was a negative, well, they do mean a lot, actually. I take that back. If this was a negative 7 1/8, and this is a negative 5 2/3, negative times negative is going to be a positive answer. It's the same answer as both of these being positive. They can both be negative, or they can both be positive, and you get the same answer. If one is negative and one is positive, when you multiply the two, when you multiply two numbers with opposite signs, you get a negative answer. Okay. This is about negative 5, it's about negative 6. It's almost closer to negative 6. That's pretty big. 5 2/3 is closer to 6, so negative 5 2/3 is closer to negative 6. 7 1/8 is closer to 7. What's negative 6? Well, just 7. What's negative 6 times positive 7? Negative 42. The answer is going to be about negative 42. This has a bigger magnitude than this. Positive divided by negative is a negative answer. It's going to be 1 something. So let's see. So that's kind of some of the arguments that go on here, guys. Forgive me a second here. Let me just check really quick. Okay. So as we look, let's take a shot at these one by one, I guess you could say, you guys. Let's take a look at the first one. Call this the first one. Call this the second one. Call this the third one. And like I said, people have been around me. Depending on the classes I've taught and where I've taught them, you're going to see some of this. So, but I think it's potentially useful to a lot of people if you want to just kind of review some of this stuff. Let's look at number 1. For number 1, you've got negative 5 2/3, and you got 7 1/8. I will block this off. Go 5 times 3 is 15. Here we go again. Let's try it. 5 times 3 is 15, plus 2 is 17. That's 17/3. The negative they put on top, I got to talk to you about that as well. When you get negative 5 2/3, negative 5 2/3, you know that means negative 5 2/3. So you got to block it off and get the answer. When you get the 17 over 3, that 17 over 3 has a negative right in front of it. Right in front of it. Right in the middle or on top, but it's right in front of it. You can write it like that, or write it without the parentheses and put it in the middle, or write it with the negative up here, or write it with the negative on the bottom. You can only put a positive divided by a negative as a negative answer. Positive divided by negative is a negative answer. Negative divided by positive is a negative answer. And a positive divided by positive is a positive answer, and throw the negative out in front. All of these have a negative answer, and they're the same answer. It doesn't matter where you put the negative. There's only going to be one of them, though. It's in the middle. It can be in the middle, on top, or on the bottom. On top is usually pretty easier to have the negative sign. So you got 5 times 3. 5 times 3 is 15. 5 times 3 is 15, plus 2 is 17. 17 over 3, that's negative 17 over 3. 7 times 8, 56, and 1, 57. 7 times 8, 56, and 1 is 57. You got to get now we said it was going to be 1 something. Let's see here. Usually what they do when they do these, you guys, you try to get the same denominator. If you multiply by 1, you don't change what the number is. A special kind of 1 is anything over itself. By what would you multiply 3? Well, what is 3 times 8? It's 24. 3 times 8 is 24. How would you get 24 if you multiplied by 3? How about a special 1 called 8 over 8? How would you get 24? By what would you multiply 8 to get 24? How about 3? 3 over 3 is 1. If you multiply anything by 1, it stays the same as it was. If you multiply anything by 1, it stays the same as it was, and you were doing this. 8 times negative 17 is negative 136. 8 times 3 is 24. 8 times 3 on the bottom, 24. 57 times 3 is 171. That's some pretty big numbers here, guys. What's going on, you know? But let's see what's happening here. The big thing is, guys, whenever you multiply fractions, I know there's cross cancellation that can happen. Let's not go there right now. Yeah, you can cross cancel stuff and it's fine. It works. But you can say here, let's multiply the numerators across, get a new numerator. Multiply the numerators across, get a new numerator. Multiply the denominators across, get a new denominator. Do the same argument here and get this. Okay. You always, when you do addition or subtraction of fractions, once you have the common denominator, you copy it down. You leave it. What is negative 136 and positive 171 when you add them together? Negative 136 and positive 171, I think it's like 35. Comes out 35. Well, our guess was, remember our argument was, you know, you add the two, this one comes out on top by about 1 something. By about 1 something when you add these two. We saw, you know, 7 something, take away 5 something, it's going to be 1 something, close to 2, whatever. So I got this right here, 35 over 24. 24 goes into, this is fine. This is called an improper fraction when the numerator is bigger or as big as the denominator. It's called an improper fraction. 24 goes into 35 one time. 24 goes into here. 24 goes into here one time. Difference of 11. You know, that's, you know, if that was 12, 12 over 24, 12, if that was just one more up top here, 12 over 24 is a half, it'd be 1.5. Well, it's close to 1.5. It's 1 and 11/24. Okay? So that's basically the argument. Okay, so that's number 1. That's how number 1 played out. For number 2, look at it. Ain't too much of a difference. I mean, it's, you know, there's a lot. I use kind of the same numbers here. Kind of play the game if you don't mind. And let's see what we can say. And I just erased what I did not want to erase, guys. Okay, well, that's what it is. Let's go for it again. Here's 2, and I will try not to erase it. So we got 5 2/3 minus 7 1/8. Now, how's that going to play? Well, it's going to play the way we know it's going to play, guys. We've talked about, you know, we talked about A minus B is A plus the opposite of B. We've talked about that. A minus B is A plus the opposite of B. Minus 5, or negative 5 2/3, minus negative 5 2/3, negative 5 2/3 minus 7 1/8. Minus 7 1/8 is plus a negative 7 1/8. Well, here we go. Block this off. 5 times 3 is 15, plus 2 is 17. Let's do it again. We did it. Block it off. We know all the tricks now. 5 times 3 is 15, plus 2 is 17. That's 17 over 3. Oh, I was a negative. Okay. Here we go again. Block this off. 7 times 8 is 56, plus 1 is 57. Okay, well, we're going for a common denominator here somehow. It's going to be something over 24. We did it last time, right? And it's going to be something over 24. Our guess was the thing was going to be like a negative 12. The way that thing was playing out. Negative 12, maybe a negative 13, whatever. Because I lost 5. I lost more than 5. And then I lost, you know, you took more than 5 away from me. And then you took more than 7 away from me. What did you take from me? More than 12. So let's see how it plays out. If you take this, multiply by a special one called 8 over 8, 8 times 3 is 24. 8 times negative 17, well, this is no surprise. It's 136, right? And over here, you know, what would you multiply 3 to get 24? It's going to be 8. Special one's 8 over 8. You got to make the move based on what gets you to the 24. By what would you multiply 3 to get 24? It'd be 8. 8 over 8 is the special one. You don't change what this is because you're multiplying by 1. By what would you multiply 8 to get 24? 3. Special one's 3 over 3. You don't change. This fraction doesn't change, just gets a different look because you're multiplying just by 1. You're multiplying this fraction by 1. You don't change what it looks like. Me saying to you the number 2 is 2. It's 2 over 1. Yeah, it's also 200 divided by 100. 200 over 100 is still 2. I can give it a different look. If I multiply it by 100 over 100, 2 over 1 times the fraction 100 over 100 is 200 over 100. It's still 2. So that's kind of the logic here. You're not changing anything. 8 times 3 is 24. 3 times 57. All of this stuff, yeah, I guess it's supposed to look familiar. We're using a lot of the same numbers, right? We're using the same numbers. Negative 171. Let's go. Add the tops. If you add two negative numbers, the result is even more negative. Sounds good to me. How about 300? I'm getting, well, let me see here. I want to say 307. Yeah, I think it looks like 307 to me. Negative 307. Interesting. Okay, let's get a read on this. Negative divided by negative number divided by positive number is negative answer. So okay, I know it's going to be a negative answer. All right. Throw it out the window. Now let's get 24 into 307. Well, 24 is about 25. 25 goes into 100 4 times. There's 3 of those 100s. It goes in about 12 times. Do you need more than that? I don't know about that. 12 times, luckily, like I said, I don't think I brought a calculator with me, so we might have to go a little old school on this one. 12 times 24 is going to be 288. Yeah, it's about right. So it goes in there, like I said, let's not sweat the negatives right now. You know it's going to be a negative. Let's just try to see what we can say here, if we can say something here. This is going to be 12. I'll throw the negative on there in a second. 12 times 24 is 288. 288 is how far short of 307? 12 here, 19 here. Okay. 19 over 24. We said it was about, you lost about 12, you lost about 13 when you did it. And that's that. And it's just same kind of argument, you guys. We try to erase. I mean, I wrote some of this stuff down. It's a little easier to look at if you just don't have to keep erasing it, I guess. Let's do number 3. Let's do multiplication. Well, guys, I don't want to completely beat this thing to death. We don't have to at this point. We know a lot. I mean, we know what the numbers come out to. We know the arguments to get it there. Usually when there's mixed numbers, you want to make them into fractions. There's other ways to do this. I don't know if that's a route I want to take right now. I want to give you something that for sure is going to get you through this. So we said this was going to be about negative 42 at the end of the day. Evaluate this as a fraction. Evaluate this as a fraction. And how do you do this? Well, there's cross cancellation. There's a lot you could do here. There is cross cancellation you can do. 3 goes into 57 19 times. So that works. That works actually pretty good. Let's pretend I didn't see it. Now, that's a little bit of a mess if I didn't see it, but let's see. Whenever you multiply fractions, you multiply the numerators across, you multiply the denominators across. And this is going to be a little rough. Let me think. do some of this in my head, I guess you could say. A negative times a positive is going to be a negative answer. I'm just going to do positive answer first to kind of get an idea of what I want to say, and we'll take it from there. If it was times 20, it would be 1,140 minus 171. 1,000. Let me think here. 969. I'm getting 969 here, and I'm not really believing it. But so let me see, and that'll be a negative. And then 3 times 8 is 24. Not sure I entirely believe it, but let's take a look. Let's say you don't have the calculator. You got to do it. You got to get it right. Let's see what we got here. We go here. That's 49. This is 35, and 4 is 39. Here's 0. Yeah, that's surprisingly. Yeah, looks good to me. Let's see here. 35, 39. Yeah, right. This, 49. You got it. Looks good. So, yeah, it should be the way it is. So we got this. This is kind of a little bit of a mess. So what do we say here? We said about 42. So I don't know. I'm doing the division here. I know it's going to be a negative number. Let me just not worry about that as much. Let me just see what I can do with 24. Let me think, guys, how I want to do this to actually get the answer here. 24 goes into 96 4 times, actually. And that's 0. Bring a 9 down, doesn't go into here, that's 0. The 9 comes down again. 40 and 9/24. So negative 40 and 9/24. How sharp are we, guys? How sharp are we when we do this? That's it. That's true answer. Tell you what, cross cancellation also works. Does 3 cross cancel into here and give you a 19? Yeah. Multiply the tops across and let's see what happens. Negative 17 times positive 19. I know it's going to be negative on top, so let me just kind of do some stuff in my head right here, guys. 340 minus this is 320. So it's going to be negative 323. If you multiply these across right here, you're going to get, let me just check that really quickly, guys. I don't want to give you too much of a bad move here on this. Yeah, it should be right. Negative 323, and then 1 times 8 is 8. Does 8 go into here? That's a good question, I guess. 8 goes into here. It's going to be a negative number again. How about negative 40? Wait a minute. Yeah, in fact, I got to give a better answer than this. This is true, but this is better, what I'm about to give. 8 goes into negative 323. Negative 40, let's forget the negatives, guys. I mean, the negatives you can forget. Negative divided by positive is going to be a negative answer. So it's going to be a negative answer. Just forget that for now. Forget the negative. Does 8 go into 320? Does 8 go into 323? 8 goes into 323 8 times. 8 goes into 323 40 times. 8 times 40 is 320. 3 left over. There's your answer. End of the day. That's the answer if you throw a negative in front, of course. 9/24, you guys, and this is not acceptable in a lot of places. You got to do better. 3 times 3 is 9. 3 times 8 is 24. 3/8. My mistake. As I said, we're going to make mistakes. Let's try to correct them, and hopefully we come out of it okay. Hopefully we get lucky. We come out of it all right, right? But try not to make the mistakes. It's the best thing. So we got the answer here. Either way you go, the cross cancellation works pretty good. Okay. That was 3. Let's talk about 4. So here's 4, guys. We said this is going to be about -1 or something like that. Now, we've messed with these mixed numbers enough, we've got them memorized as how they look as fractions by this point, or at least we can easily make the moves. 7 times 8 is 56, and 1 is 57. Divided by, block this off, 5 times 3 is 15, and 2 is 17, 17/3. A fraction divided by another fraction. A fraction divided by another fraction is the first fraction, the one that's being divided, left alone, multiplied by the reciprocal of the second fraction doing the dividing. Say that one more time. A fraction, you got A over B, you got a fraction divided by another fraction, that equals the first fraction multiplied by the reciprocal of the second fraction doing the dividing. A fraction divided by another fraction is the first fraction multiplied by the reciprocal of the second fraction doing the dividing. This times this is -171. 8 times 17 is 136. Again, we use a lot of the same numbers, guys, obviously, so there's some similarities here. It's going to be a negative answer. This goes into here. Throw the negative out the window for a second. 136 goes in here. 136 goes into 171 one time with 35 left over. That's it. The big thing is, it doesn't matter the signs, guys. The symbols don't always show the signs. These give me negatives all over the place. A fraction divided by another fraction is the first fraction left alone, multiplied by the reciprocal of the second fraction that's doing the dividing. I don't know how good this shows up on film, so let me make it just a little bit bigger. And that's it. That's it. That's what I want to say on this. There's some other practice items that I'll go through with everyone, and we'll take it from there. Okay, thank you all for your time. Take care.